Hello. Today, in this video, I'd like to talk to you about series circuits. We're going to take a look first at Kirchhoff's laws, some simple rules that we have to follow whenever we're solving or constructing a circuit, and then finally we're going to apply those rules specifically to series circuits and then take a look at a strategy for solving some examples. So starting off with Kirchhoff. Now these two laws underpin everything we're going to do with circuits. They're very fundamental and basic. They can be applied to really simple circuits or more complex ones that we might see later in the course. But they deal with two concepts we want to know: junctions and loops. A junction is just any time when two wires or two pathways in a circuit meet. We could think of a simple junction like this, where we have one wire coming in there and one wire coming in there, and then maybe they leave like this. So we'll say that electrons are flowing in this way and where they're flowing out that way. And you can imagine more complex and more simple junctions than this one here. Now the rule that we're going to have here is that in this circuit, in your junction, the sum of the currents entering this junction must equal the sum of the currents leaving this junction. So for example, if I had 5 amps of current heading in this way and 2 amps heading in that way, I have a total of 7 amps. It means I have 7 coulombs worth of electrons heading into that point per second. It just makes sense then that 7 coulombs worth of electrons must be leaving that point every second in order to balance things out. You can't have an imbalance of electrons. This really just comes back to the conservation of mass and charge. And so if I have 7 amps coming in, I know that has to be split between those there. Now they can be split any way. A problem might say, hey, now we've got, let's say, 3 amps leaving on this particular side. How many amps are coming through this one? Because of this rule, I know 7 come in, 7 must go out. This bottom one must have 4 amps leaving there. Now, Kirchhoff's second rule is a little bit trickier, and it has to do with loops in a circuit. So let's go ahead and make a kind of a simple circuit and take a look at the loop law. So our example is going to have, let's say, a power source, and then a resistor, and then maybe a lamp, and then finally heading back to my power source. So I have made a loop in my circuit. But let's make another loop that's in parallel to that loop there. So what Kirchhoff's law says is that the sum of the voltages around a closed loop in a circuit has to be equal to 0. What that means is if this is like a 6-volt battery, that gives the electron 6 volts of potential energy. And so that electron gains that 6 volts coming around here. But then if it goes around this loop, it has to lose those 6 volts somewhere. And so those 6 volts must be proportioned between our lamp and our resistor. Similarly then, it also has to lose 6 volts around this loop right here. There's another loop in the circuit, and so that must also be equal to 6 volts. And you notice then this other loop also has that same 6 volts in my circuit there. So the sum of the voltages around any closed loop must be equal to 0 in a circuit. Okay, let's go ahead and take a look at these two laws applied to series circuits. So in a series circuit, let's just take a very simple example here with a battery and a resistor. The first factor equation we're going to have, and this is based off of Kirchhoff's junction law, dealing with the fact that you can't ever lose current. The sum of going in has to be equal to going out, is I have no junctions at all. Every electron that leaves the battery has to come back to the battery. Because of that, the current flowing through my entire circuit, my series circuit, is constant. There's no other path for it to go down. That's what makes it a series circuit. And so the current has to be the same everywhere. If I measured the current here at point 1, that current would be the same over here at point 2, which would be the same at point 3. Now mathematically, and what you'll see in your reference tables, they state that like this, that for a series circuit, the current is the same at point 1, point 2, point 3, so on and so forth. So the current in a series circuit is always constant. Now we're going to contrast that with the electrical potential. The voltages in a circuit, or the electrical potentials, will add to the total voltage. Or we also want to say, another good word for total is what's called equivalent. Total or equivalent. Now what sets your total voltage in a circuit is your power source or your battery. So your equivalent voltage is going to be, in this circuit, 12 volts. Now, this means that all the voltages in the things in the circuit must add to that 12 volts. That sounds a lot like Kirchhoff's loop law, that if we have one loop, it makes sense that everything else has to add up to that 12 volts. And so we would lose 12 volts through my resistor here, and we would add it all up here to 0. Now, mathematically, we express it like this, that the total voltage, or the equivalent voltage here, is equal to V1 plus V2 plus V3, where V1, V2, and V3 might be, my one resistor here is number 1, and so we'd say V1 here is 12, and that matches up with my 12 there. Now, I put a little negative there. We could put positive. I put the negative, so we say it kind of all has to sum, or you could think about that the sum of a loop has to equal that total voltage. And then finally, we've got our final law, which is a resistance law. Now this one takes a little bit of thinking. We know that resistance is related to potential and current. Voltage is I times R. So our electrical potential is the current times R. If I is a constant, then if this increases, the resistance has to increase as well. So each time I add another potential up, I'm also adding a resistance in my circuit. And so the equivalent resistance, the resistances in my circuit, also add to the total resistance. And we often call this resistance an equivalent resistance. It's the total resistance of all of the things in the circuit added together. So if I made another simple circuit, let's say it's one here with a resistor there and a resistor there. I've got a 12 ohm resistor there and an 8 ohm resistor there. This circuit has an equivalent resistance equal to those added together, or 20 ohms. It would be the same thing if I drew a circuit that just had a 20 ohm resistor. Functionally, those circuits will act just the same. Now, the last thing we need to know about series circuits is if one device turns off, kind of like with your Christmas lights, if you take a bulb and it's all wired in series, what happens to your Christmas light strand? They all go out. And so if you have a series wired Christmas lights, if one device turns off, all devices turn off. This is because that current has to go through every device. And so if you turn off one device, the rest of them won't be working anymore because no current can flow through the device that is off. Let's take a look at a few examples here. So my first example, we have a 2 ohm resistor and a 4 ohm resistor are connected in series with a 12 volt battery. If the current through the 2 ohm resistor is 2 amps, the current through the 4 ohm resistor is, well, what are the greatest things to do? Whenever you get a problem that involves circuits, if they don't have a picture already for you, you should draw a circuit diagram to show your circuit here. So I've got a 12 volt battery and 2 resistors wired in series, 2 ohms and 4 ohms. Now we know the current going through this resistor is 2 amps. So by that law that says that in a series circuit, all of the currents are equal, we know the current is always I1 equals I2 equals dot, 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 dot. I1, that I1 through my 2 ohm resistor, is 2 amps. Well, that means that the current everywhere is 2 amps. The current through number 2 is 2 amps. And so my answer here is 2 amps. Okay, let's take a look at another example here. In a circuit, we've got 2 4 ohm resistors that are connected to a 16 volt battery in series. We want to know the power in this circuit. Well, to find my power, we know power is V times I. I know the voltage, it's 16 volts in my circuit, but I don't know the current flowing through my circuit. Now, we could solve this a few different ways, but I want to introduce one of my favorite ways to solve circuits. That is using a VIRP table. V, I, R, P. The way you set up one of these tables to solve a circuit is you first draw your circuit out. We know we have a 16 volt battery wired up in series to 2 4 ohm resistors, 4 ohms there, 4 ohms there. Now, to set up your table, you then list all of the loads in your circuit. And here, we just have 2 resistors, so we'll call it resistor 1, resistor 2. Then we've got our total for our circuit. So this is how we'd add up the equivalent part of our circuit there. So you could also call this EQ rather than total. Now we know the total voltage is always set by the power source, the battery. So the total voltage, or the equivalent voltage, is 16 volts. That's got to be split between R1 and R2. Our current, we don't know, but that's something we need to find the power, or we can use the power column over here in our VIRP table. But we do know the resistances of R1 and R2. We've got 4 ohms and 4 ohms. Now because both of those are 4 ohms, and this is a series circuit, resistances add. So if I've got two 4 ohm resistors, that's the equivalent of an 8 ohm resistor. So now that I have my total voltage and my total resistance in my circuit, we know Ohm's law can help us solve for the current. So across any row of your VERT table, you can always use Ohm's law to solve for one of the variables you don't know. So since I know the voltage is 16 volts, I want to solve for the current. I know the resistance is 8 ohms. My current in this circuit is going to be equal to 2 amps. So I can put that in my table there. So Ohm's law applies across a row in a VERT table. Now, one of the greatest things ever is that because it's a series circuit, I can automatically fill in that entire column for current because the current is equal everywhere in a series circuit. From here, I've got my table solved because I can use Ohm's law, knowing that V equals I times R, to solve for the resistance of, not the resistance, the voltage of both resistor 1 and resistor 2. 2 amps times 4 ohms gives me 8 volts. 2 amps times 4 ohms gives me another 8 volts through resistor 2. Now you're going to notice one of the that last circuit law holds true for this circuit. We know the voltages must add together. 8 volts plus 8 volts gives me 16 volts. Finally, we want to find the power in the total circuit. You actually can find the power through any particular device. V times I would be 16 watts. V times I, 16 watts. V times I, 32 watts. You'll notice the powers also add in this circuit here. And because it wants the power in the circuit and not through either of the resistors, we're going to go for 32 watts here. But I've seen questions where they might ask you for the power just through one resistor. So you want to make sure you know exactly what you're looking for here. Okay, let's go ahead and apply this to one last problem. We have a light with 50 ohms of resistance in a series with a variable resistor to a 20-volt battery. The light can only take 0.1 amps of current. So to draw out my circuit here, 20-volt battery hooked up to a light that is 50 ohms, and then a variable resistor right there. Setting up our VERT table again, we've got VIRP, not another R, P, and then I'm going to do light, resistor, and total. Now, you can look at the questions down here, but before I do that, I might just go ahead and solve my table, and we'll see how easy these questions become once you've filled this out here. So once again, I know my total voltage is 20 volts. I know that my light has a 50 ohm resistance. I don't know the resistance of the variable resistor, but I do know the light can only take 0.1 amps of current. So I want to solve this with 0.1 amps. Well now, using Ohm's law, 20 volts is 0.1 amps times R. I can back out that my total resistance in the circuit must be 200 ohms. That means that my variable resistor must be 150 ohms to add at 200. Now, 0.1 amps, because it's a series circuit, applies to every different current because the currents are always equal or constant in a series circuit. That means I can solve for my electrical potential. 50 times 0.1, 5 volts, and 150 times 0.1 is 15 volts, and these add here. We don't need power for this one, so I'm going to go ahead and leave power as an exercise to you. Now it says, what's the maximum the variable resistor could be set at in order to protect the light? This actually should say minimum, because if the resistance goes up, it's only going to be better. If it goes down, though, the light might blow out because the current would be there. But we've already seen here that the resistance through my variable resistor must be 150 ohms. Number B, what's the voltage across the variable resistor? The voltage across the variable resistor, my resistor, 15 volts, 0.1 amps, times that 151 ohms we found there. And then finally, what is the voltage across the light? We found that that was 5 volts, and that's good because that adds 5 volts plus 15 volts up to my total voltage from my battery. So you'll notice they don't always have to be equal. You might have different voltages on different parts of different components in a circuit, in a series circuit. Okay, that's all for this video. Thank you all very much.